All right, let's talk about a really fascinating problem, one that's at the absolute core of things like modern robotics and avionics. How do you get a super complex system to change everything it's doing, on the fly, without missing a single critical beat? We're diving into what are called mode switches in adaptive real-time systems.
So here's our game plan. First, we're going to break down the basic challenge itself. Then, we'll look at the main strategies, or protocols, that engineers use to handle it. After that, we'll get into the really tough part, the trade-offs they have to make. And finally, we'll see how all of this affects the system's ability to hit its deadlines, which is, the most important thing. So why is this such a big deal? Well, think about a robot being piloted by a person. The operator flips a switch to put it in automatic mode. In that split second, the whole system has to just drop what it's doing, say, listening to a joystick, and start a completely new set of tasks, like navigating with sensors. How does it pull off that switch without getting confused, or missing a vital piece of data, or, well, without crashing? That's the high-stakes problem we're going to unpack.
Okay, to really get into that problem, we've got to make sure we're all on the same page. Let's lock down some of these key terms. First step, what even is an adaptive real-time system? Well, you can think of these as systems that are built for change. They're designed to completely alter their behavior on the fly, maybe because their mission has changed or the environment is different. But, and this is the crucial part, they have to do all of that while still meeting every single one of their deadlines. No excuses.
And that brings us to the main event, the mode switch. This isn't just about a system having different modes, it's about the process of getting from one to the other. That transition, that gear shift, that's the riskiest, most critical moment we're focusing on.
So how do engineers actually manage this tricky transition? Well, it turns out there are really two main ways of thinking about it, two different philosophies. We'll call them protocols. The first approach is called the idle time protocol. The best way to think about this one is the wait till it's safe method. It's synchronous, which means it's all about order. The system basically says, hold on, I'm not switching anything until all the important stuff I'm doing right now is finished. It's all about being cautious. And yeah, the process is exactly as patient as it sounds. Someone requests a switch, but the system doesn't just jump. Nope, it waits for what's called a safe idle point. It lets all the old tasks finish up what they're doing, and only then does it fire up the new mode. The top priority here is stability, not speed. And then we have the complete opposite, the single offset protocol. This one is all about speed. It's the switch at the next possible opportunity method. Instead of waiting for everything to finish, the system does a quick calculation to find the perfect moment in the very near future to make the change, and it just does it. Here, the goal is to be as responsive as possible. But here's the thing, there's always a catch, right? You can't just pick one without giving something up. This is the classic engineer's dilemma. You're forced to balance goals that are totally in conflict with each other.
And here's the first big one, speed versus rhythm, or in engineering speak, rapidity versus periodicity. I mean, of course you want the system to switch fast. That's high rapidity. But if you switch too abruptly, you can completely throw off the system's regular, predictable heartbeat, that timing that keeps everything running smoothly.
And there's another conflict, rapidity versus sampling preservation. A fast switch is great, it feels responsive. But what if it's too fast? Let's go back to our robot. If it switches to automatic mode instantly, it might do it right in the middle of taking a sensor reading. It could miss that data entirely or just get it wrong. And suddenly, it has no idea where it actually is. That's a huge problem.
So, keeping those trade-offs in mind, let's put our two protocols head-to-head and see how they really stack up. This table really tells the whole story. You can see right away the idle time protocol is the absolute champion of periodicity. It keeps the system's rhythm perfect. But the price it pays? It's slow. The single offset protocol is the mirror image. It's crazy fast, but it puts that stable rhythm at risk. You just can't get the best of both worlds.
Which brings us to this key quote from the source material. It says that these different protocols are really just characterized by the subset of requirements they privilege. And that's the big takeaway. There is no single best way to do this. It's an engineering choice, and it all comes down to what's more important for that specific mission. Is it absolute safety and predictability, or is it lightning-fast response time? Okay, so we've picked a protocol, but what does that decision actually do to the system's number one promise? Its guarantee to meet every single deadline. This is the critical question of schedulability. Right. The key thing to remember is that a mode switch isn't free. It's a real task that uses up CPU time and creates this messy in-between state that has to be carefully analyzed. A safe protocol like idle time might actually cause a big spike in the system's workload. A fast one has to be calculated perfectly to make sure tasks don't run into each other. The ultimate goal for an engineer is what's called a schedulable mode switch. That's a transition that they can prove mathematically will never cause a single deadline to be missed. So, let's wrap this all up. What have we learned? Adaptive systems use mode switches to change what they're doing. There are two main flavors: synchronous, which waits to be safe, and asynchronous, which goes for speed. The choice between them is always a trade-off between being fast and being predictable. That means the best protocol is different for every system, depending on its mission. And no matter which one you pick, you have to prove that the switch itself won't break the system's timing.
And I'll leave you with one final thought to chew on. We've talked all about how to manage these transitions, but what happens when the protocol, the safety mechanism itself, fails right in the middle of a critical switch? What happens when the thing designed to prevent chaos causes it? It's a pretty deep question, and it opens up a whole other level of complexity. Anyway, if you found this breakdown useful, please do me a favor and hit like, share, and subscribe for more explainers like this. Thanks for watching.